Good afternoon again. I hope you had a good input from the first sessions. So let's go into now the breakouts here. And I would like to take you through how we have been working with our direction of how to do your journey then. And I think the key point for us, it's what we heard in the beginning here. Don't just replace a PTO with an electrical motor and size it. I would say take the sizing of the motor in the end of your design process. It's so important that we really understand what we would like to do with application, with the machines and so forth. So that means really the system requirement will play a very, very important role. And also how all the trade-offs need to be in that type of system design. So you can see in this triangle here, it's a trade-off, what we need to have the focus on, and understanding why we select different solutions in the circuitry. So you can see efficiency, if that is a key element, that can be how the work cycle are designed, how big energy storage you need, and so forth. But maybe the modularity is a key element to be able to have a flexibility in the manufacturing side, really about it's not one-way architecture on the system. And also in the end, serviceability when it actually coming to the end user, and these machines need to be up and running all the time. So it's a lot of different trade-offs you need to do to having service people, what is skill set in this technology as well. But again, everything really starts to understand where is the energy go. Is that waste or useful work become very, very important in your design process. And what we have seen, we need to do proper work according to the baseline, to understanding where is the energy going according to flow and pressures, forces, and so forth, what is needed. So we understand what is useful work and what is waste. We also can see the total efficiency will also be trade-off on the installed technology as well. So focus is important for that, and a clear picture on the requirement. And also evaluate probably option A, B, and C become very important. It's a trade-off. And that trade-off will give us the guidelines where to pick the hardware you would like to have in your solution. So how do we do this then? I would say this is a picture on our test yard, our test field, what we have in Sweden. There we can actually see and define what is a work cycle, monitoring that, and you can repeat that as well if you want to. But the key element is to do acquisition on the machine. So we have a very good understanding really where all the energy goes before we start with the project. And if we have all the load data, that means everything what have been as a energy for the motions, take all that into the simulation model and you can see where it goes. And then define and focus on really what is useful for you when you do the trade-off. So this is an internal project we did. And for some of you what saw that in the beginning, it's a key element to see where the losses go and really how to break it down in the different bits and pieces. The hydraulic system will actually play a big area where you will find the losses, of course. So this is an overview. We talk about electro-hydraulic pump. We talk about electro-hydrostatic activation and also the mix between the two. But if we see now and just focus on the electro-hydraulic pump, you can see it's a power on demand, what is a key element. So that means no idle anymore if this is not needed. And also you can see how much power you need to have as well. Still, the energy only go in one direction, from the battery out to the motion itself. So if we now would like to do something higher up as an energy saving system design, we need to take another level up. And here you can see electrohydrostatic actuation. First of all, we're using a very, very high efficient pump, what can operate in the 4-quadrant operation. So you can have pressure on both sides, you can turn it backwards, forwards, whatever you would like to do. But the key element, you remove all the throttling losses completely. So that means now you can actually do all the energy what you're taking up. If the battery can handle it, you can also get a lot of battery back into it. And of course, that will expand the lifetime on the life circle on your work cycle itself. And here, in reality, is probably a mix between the two. So you can see here, it's an image about, first of all, combustion engine, as we can use as a generator. And then we can also see all the batteries actually going out to the different source. So you can see electrical motor using the batteries all the time. So you can have either an EHA or an EHP, as we just talked about a minute ago. So what will that give us? If we now go into construction, you can see we have some applications where we have utilized this technology on, material handling, the same thing, and also on the refuse side. So what is important, that is actually to see how far up can we come into reducing, the energy or increasing the energy efficiency, of course. So the key element of it starts with a pump. So we know where the electromechanical, what they would like to spin. And Parker have so much different choices to offer you here. So you can see here we actually having key criteria, what is a good input from your system requirements. So we can talk about duty cycle, it's a key element for us when we're designing what type of pump technology you would like to use. We also see the efficiency. How important is the efficiency in your application? And in the end, the noise as well. When you remove the noise level from the combustion engine, the focus will go to the hydraulic system, and that become more and more important from the complete system design as well. So we talked about EHA, EHP, and again, it's really about efficiency. It's where you can take it in, take it out, and that is a key element of the system design itself. Similar is really about an EHP. But from an electrohydraulic pump, it's not only about what you bolting together. That is how much you can do also on the software side. How to spin the pump become important, what we will talk about in a second. So the choices is multiple. You can see here we have variable pumps, fixed pumps, we can have a vane pump, and we can have a gear pump. You pick, depending on your needs, in your requirements. Key element that is, it's a part of the trade-off. So, if we're moving from the pump and now continue into the valve side of it, you can see the next generation valve, what actually have sustainability in mind. You can see it's about the material what gets used. It's about how to reduce the energy losses inside the valve itself. How we can improve really the productivity by smart functionality, but also how we can do even smarter functionality with individual metering capabilities. And you can see here, that have been a major focus. You can see the images, so only the small piece make a package very, very efficient for the market as a next generation solution then. And if we actually see here on the lower right side, we talk about this individual metering. What is a fantastic result if you actually are focused on energy savings. And you can see here I have the bar graph setting up as a named of our traditional load sense valves for the mobile market. It's K170, what we have been using in this trade-off testing. But also the IMHC, what stands for individual metering hydraulic compensated solutions. And the results is fantastic. You can see if we compare it with a traditional work cycle, we're actually dropping the energy by 8%. So you're saving 8% from an energy standpoint. Even more important, that's really about the pump pressure actually get lower. So that means by now oversee the circuitry all over the place, you can probably have more savings if you need to and if you can, and be adaptive into the circuitry. But even the most important of everything then, the productivity is the same on the machine. So that means no trade-off on productivity, and that is the key point for you. So, to be able to do all these, control principles make it very, very important. And I showed you that before. We have a tradition to really design the system on the peak power. What actually become really, really off the track or off the important part on the design for the future. Now we talk about average energy, average power in a motor. And that's where really high cooling capabilities on the electrical motor will play a very significant, important role in the system design. Over-torque it when you need the power, make sure you can cool it down when you can rest a little bit. And by having all this data in front of you when you do your control principles, you can see traditional, you have been all over the place, but now you can see it can be optimized. So by all of this, you can see here that all the input become very important from a control system standpoint. We need to increase the capability to monitoring different pressure controls in the cylinders and also on the pump side and so forth on the whole circuitry. And not more important is the communication buses, what need to be supported. Same thing on the output side, equally important that you can of course control it, but you also have the capability on diagnostic to fulfill the safety functionality of it. And then, of course, continue up to the human interface, you can see what's going on, setting different type of behavior on the system, what is required is key element. So if we then continue with the control principle itself, we talked about the valve side. To have an input to the control principles is to understanding if this is an open center valve, is that the closed center valve, is that the load sense valve. It becomes really important to choose the right control principles later on. The pump, the same thing. How to spin the pump. Is that a fixed pump? Is that a variable pump? Make a big difference when you're controlling and find the optimized solution. And of course, the inverter side. It's not only about the torque control and the speed control. Of course, that is important, but it's really about how to make sure the hydraulic function acting as it should from a pump controller side. So, we talked about this 2x2 layout here. We have fixed displacement, we have variable displacement, and how to control it by the speed become very, very important. And here you can see a picture on how to make sure that you are in the spot what you would like to be, whatever it's a torque or is that controlled by a speed, and riding the curve become very important. But also when you're talking about keeping the small distance on the metering pressure over a load sense valve, when we spin it and we do that, the motor to the pump as a fixed displacement pump, need to make sure you have the required metering measurement. Even if you are boosting your system or lowering the system, So the power on demand is not only how to spin the pump, it's also about how to control it. The same thing, it's really about if you go into keeping a certain level, and of course in the torque setup as well. So motor sizing become important, of course. So in this case, now when you have designed your whole circuitry and the whole system, now you can go into to see how you can design your solutions on if you need to have a generator, if you need to have a pump, what is on the implement side or running as an EHP, if you need to have an EHA, where you're really driving the functionality with the energy recovery, what is coming back. And of course, the propel or the tractions on the machine. And everything together will make the sizing key element and what is available in your battery storage, of course. So the different subsystems become very important where you pick and how to do the motor sizing, especially in the combination of each other. So as a summary of it then, you can see here, if we then continue with all the building blocks, I would like to summarize the importance of electrical motor, what have a very high energy compact solution. I would like to summarize it with an inverter, what really have not only the very tight connection to the electrical motor, where you can do parameterization settings as an optimal way. Both of the components are matched together with including of all the capabilities what we have as a function block inside the drive. We talked about the control system where we have all the functional safety built into the control system. The capabilities where we have capability to insert and integrate it directly into model-based coding. We have the hydraulic valve solutions where we have all the capability with smart functionality. We have also where energy efficient solution capabilities as well. And of course, the variety on the different pump settings and the pump solutions, what we talked about a minute ago. Equally important, what you can also hear later on this afternoon, is the thermal management. And that become more and more important. It's so much new for us, different medias, different temperatures, what actually are existing. But if you have a very efficient system, the sizing of thermal management become key, because you cannot use what you are used to when you have a combustion engine. And all these bits and pieces come together. The whole business case itself is not about only the technology you install from a system side. You need to include the battery cost as well. It's a combination what you can saving on your system side with all the hydraulic solutions with what you would like to have. In combination, how low can you go on the energy storage side as well. So that is really the key element as well. And you can see as a summary of all this, we are spending more than 15 years about electrification by concept proofing of a lot of, I would say, good and bad. A lot of mistakes as well have been made, but that have gained us a lot of experience. And also having the opportunity to have dedicated product for the mobile market is really, really good. So as you can see, we can just offer our experience, share our knowledge, what we have gained, to reduce your time to market. Thank you.
Thank you so much. Very short, what should you spend the most time on in your electrification journey?
I think this is what we talk about in the beginning here, understanding your customer needs.
Yeah.
And all the trade-offs, what you need to do, because we have so many different options to choose from. So having a very clear system requirement is probably the key for a successful project.
Thank you so much.